Thank you very much for inviting me. Thanks, Agios, for inviting me for this event. I'm very pleased to have the opportunity to show this ongoing project and some of the preliminary results we are already getting. So the name of the project is MedEOS. It's focused on the Mediterranean. It's a part of the ESA regional initiative for the Mediterranean. And the focus is on land-based pollution assessment and how to monitor that in the Mediterranean coastal waters. So the main objective of this project is to develop and produce daily high-resolution gap-free maps of a set of experimental Earth observation-based water quality products. And the main idea is that we employ data fusion techniques to combine the high temporal resolution of Sentinel-3 with the high spatial resolution of Sentinel-2. As probably most of you know, Sentinel-2 is a spatial resolution of about 20 meters, but it only covers the Mediterranean around every 5 days, while the Sentinel-3 is a daily product. We have daily results from it, but it has a 300-meter spatial resolution. On the other hand, Sentinel-3 also has a better spectral resolution since the sensor was designed to look at ocean color. So anything that we try to derive from Sentinel-2 requires some specific parameterization and correction for the different spectral bands that are available. And like I said, this is being funded by ESA. It's a 2-year project, and we are now right in the middle. And here is the portfolio of the project. So our intention is to develop this set of EO direct derived water quality products. So directly deriving the parameters from reflectance at sea level. And the parameters that we're trying to derive here are total suspended matter, turbidity, chlorophyll concentration, SEC depth, and color dissolved organic matter. And as you know, these are quite standard parameters that are used in water quality monitoring. And we have also a lot of products out there that already perform already delivers these parameters from Sentinel-3. So what we're doing is trying to bring, like I said before, the best spatial resolution from Sentinel-2 in a daily product. Also, from these results, we can also derive more indirect water quality parameters. So here, we're looking to aggregate this Earth observation data with numerical modeling, in situ measurements, and statistical analysis, and also some artificial intelligence approaches in order to derive a set of indicators. So fecal bacteria contamination indicator, eutrophication indicators, harmful algal bloom indicator, and a global and environmental anomaly detection based on machine learning and looking at a longer time series. And finally, we also want to do the river plume monitoring. So the idea is that we trace the river plume all around the Mediterranean coastal waters. And how we're doing this, we're doing with this very strong consortium. So we have different institutions here. As you can see, some of those are listed as service providers. So these are the partners that are actually developing the solutions. And then we have the pilot leaders, because we have a first phase of the project, we'll be developing the solution for specific pilot areas across the Mediterranean. And we have these institutions that are leading the contact with the engaged stakeholders and end users in each of these pilots. And finally, we have Demos as project leader doing all the management, but also doing the integration of the solutions in a single platform and providing all the infrastructure. Like I said, this is a 2-year project. Here, I actually got the date. I see now that this is wrong. It's until March next year. So it's not March 22, it's March 23. Like I said, we have 5 different pilot areas. One of them is in Tunisia. And we have engaged users for each of these areas that will be evaluating these products. We had a user consultation phase already in the beginning of the project, in which we have the individual interviews with each of these end users, but also with UNAP map. And we also did a very complete literature review, and this allows us to derive specifically more than 120 specific user requirements to understand how this service should be deployed and how the information should be delivered to the users. And in the second year of the project, that's where going to cover not only those 5 pilot areas, but we're actually covering all the Mediterranean coastal waters. So this is a much more data, much larger data set. And it is also going to cover a full 3.5-year period. So in the first phase, we're only delivering 3-month periods for each of these pilot areas, but now in the second year, the intention is to have a complete product. So between one phase and the other, that's where we want to have some impact assessment and understand from the users' experimentation with this data, getting some feedback, getting some validation to understand how they perform against their own their current approaches. And then we'll adapt the products to that. One of the key aspects is actually the resolution, that the final resolution of the products is still under discussion. So like I said, there was a consultation phase in which we derived a lot of requirements already from review of existing documents. We had the workshop with each pilot area and also an workshop with UNAP map. And this took us to this large number of requirements that are then driving all the development of the services. And some of the interesting results we got in this consultation phase, so looking at the type of data that these end users are currently using, we see that there is a predominance of in situ sensors and laboratory analysis. So that's actually sampling in the coastal waters and then doing this analysis. Very little use of satellite data. Also, the motivation for for collecting this data, for doing this monitoring of coastal waters, is mostly on natural resources monitoring, but also for operational constraints in some cases, like a city in France and others that also have operations ongoing. And finally, of course, the environmental regulations are also a very strong driver for collecting this sort of information. Here we evaluated also the interest of these users, how they want to be, how they want this information to be fed to them. So mostly through a web-based browser, a web browser job portal, but also some users manifested the intention to have this data integrated in their own GIS systems. And here also a graph that shows a bit of the high interest that each of these products have raised among these users. So it's not so easy to see, but you see that most of the points are quite high. So the interest is quite high for all the products. Another interesting aspect of this project is regarding the way that's deployed. This is not an operational project, so it's not like the data will be constantly being produced, but nevertheless, it is a large data set that has to be produced over a long time span. So this requires a very specific sort of deployment using cloud infrastructure, and we're actually using different cloud providers here. So we have some of these processors that are deriving the information from Sentinels deployed on CreoDias, which is a cloud provider that actually offers the option to access this data, Sentinel data, locally, so we don't have to download the data. But after we generate the products, those comes to a catalog from the project's own system, and then the rest of the process takes place on Cloud Sigma, which is a cloud provider that has better deals in terms of cost benefit. So that's why we have most of the analysis in the other processors, and even the geoportal hosted in this other cloud provider. So this is a complex supply chain. As you can see, there are a lot of dependencies from outputs from one service becomes the input for the others, and then we also bring outside other data that from different sources. So in that case, it requires a deployment on this service for you. This is Deimos' own Earth observation exploitation platform. It's a set of modular tools that allows for the development and deployment of these Earth observation-based applications in a more rapid fashion, more structured fashion, and allows for complex deployments like this one. Our intention is to have all this gap filling, the direct services and also the gap filling data fusion part. This is all deployed and already integrated in the system. The rest of the system, the indirect services and the web portal will only be deployed in the second phase. So for the first phase, the results from indirect water quality are being generated offline, not in the system, not in these cloud resources. So here are some preliminary results, just for you to understand a little bit. There is already one product from Copernicus that provides these water quality parameters derived from Sentinel-2 in 100-meter resolution. These are daily products coming only from Sentinel-2, so it requires a lot of interpolation, both in time and space, because of course you have the problem with the clouds and the missing data here. Nevertheless, this is already a standardized product in being offered by Siemens, and it's being used as a benchmark for what we're delivering here. So anytime that we produce things, we're comparing to this. And in the bottom line, you can see results from both Sentinel-2 on the left and from Sentinel-3 on the right. So like I said, Sentinel-3 is the sensor that was designed for ocean color. So in theory, these results from Sentinel-3 are more reliable, but the resolution, the spatial resolution, of course doesn't offer the possibility to cover and to understand some small scale process, which you can see much better here in the Sentinel-2 image. And this, I didn't say, but this is turbidity results. This is the turbidity results. This is another result. In this case, is chlorophyll concentration for Mar Menor, an area in southeast of Spain. As you can see, again, we have the product coming from Copernicus, a product coming from Sentinel-2, a product coming from Sentinel-3, and you can see there are large difference between Sentinel-2 and Sentinel-3, and this is due to that different reflectance levels that we have in different bands, and the band distribution, of course, with these sensors is different. So what this is indicating that we have to do a lot of adaptation in order to use the chlorophyll algorithms here for Sentinel-2. So we're actually deploying two different algorithms used for more turbid and less turbid waters, and we have an automatic decision system that allows for choosing each of these algorithms, looking at the turbidity of the water before that. Here is a preliminary result of gap filling. So that's we are using the DynOff. It's quite a proved algorithm for interpolation, gap filling, and eliminating the problem with clouds. The only particularity here is that once we apply it the first time we detect some outliers caused by the interpolation. So we have to remove the outliers, which are here depicted in pink, and then we apply DynOff again. And that way we have a better results, more coherent results. That's for gap filling phase. And then for data fusion phase, here are just some results. For the first one on left is the Sentinel-3 image, the original image, and the second one is derived already by combining this with Sentinel-2 data. It's quite a complex algorithm that's being used. Also, an algorithm that was developed for land application is called StarFM. And but the problem is this was developed for land applications, assuming that there is not much change within the week that we don't have Sentinel-2 data. And this for the coastal and marine applications, of course, this is not true. The things are changing in a much more dynamic environment. So there was a full different implementation here that tries to use a database of small patches of Sentinel-3 pair of images. And by creating a database, we design a system that can actually learn from this pair of Sentinel-2, Sentinel-3 patches and use this information to reconstruct Sentinel-2 images where they are missing. So I'm not going to go into details of the process here, but the idea is that we're coming out with a different implementation to adapt this algorithm that was originally developed for land application to adapt this to marine applications. Some other preliminary results. So indirect services here already. So like I said, this is combining the reflectance levels from some specific bands in the blue part of the spectrum with the decay rate of fecal bacteria. We're calculated from models. In this case, we also use hydrodynamic information, so information from currents, and whenever we have weaker currents, then we understand that there is a higher risk of fecal bacteria contamination. So that's of course the index here is connected to those current information also. So this is a risk indicators. That's what our approach for this most of these indirect products is, to provide an indicator of risk. There's also another one for eutrophication. And finally, this one is an example from the tracing of river plumes. So the idea is that we use a complex algorithm here, also based in image recognition, computer vision, so that we can automatically trace this river plumes and then look at them on the time and see how they evolve every day. So this with the dates here, it was based on Sentinel-2. So in this case, there was no data fusion yet. So we didn't have access to the daily data, but in the final product, this should be a daily product. So we can actually see every day where the plume, what is doing. Of course, all of this will be affected by clouds. So even with performing gap filling, there will, for sure, the data will be flagged whenever we have high uncertainty levels in this gap filling step. Just wanted to end the presentation with some examples for Tunis. So this was produced this morning, actually. Like I said, we're now just starting production for the first phase, so we don't have yet the data, the gap filled and fused data. This is only data from Sentinel-2, but the idea is that we can see here how much we can extract in terms of information, how with the higher resolution data, we can actually see very small features like this discharges in the north here from the rivers. And this is chlorophyll, as you can see. Some interesting features that we can see. Also here for the turbidity map, again, not so much on the rivers in the north, but much more here. Maybe you have calmer waters. I really don't know the environment there. For sure, you have a much better capacity to evaluate these results. I was just going to show them more for the sake of how much information we can get from the high resolution data. Very similar here, of course, turbidity and now total suspended matter, TSM. It's quite similar, of course, but of course you see different units being used. SEC disk, which is the a visibility index, trying to replicate what we do in the field work with the SECI disk. And of course, this is inverted to the turbidity and the TSM. So as we go further out from the coast, we get better visibility, of course. And finally, the color dissolved organic matter indicator. So that's again connected to the turbidity and to the TSM for sure, but it's trying to actually indicate more just what is associated to organic matter. So that's what I had to show. A bit of the next steps very quickly. So like I said, we're having the algorithms are all fully developed. They're both, at least the direct services and the data fusion algorithms are already integrated. We are doing the final integration and testing right now, actually starting production next week. So we will be starting next week the production for the first year. There will be this impact assessment with users in which we will be discussing the final resolution. We initially were aiming for Sentinel 2 resolution, 20 meters, but now we are thinking about something between 50 meters and 70 meters, even 100, depending on the evaluation from these end users, together with the results from validation with EC2 data. And beyond defining the final resolution, we also want to understand from the users what is the usefulness and usability of this product. So we are quite interested to have more stakeholders and people that look at this and criticize it. We want to hear. That's what I had to show today. Thank you very much.